Right, so moving on to our next problem, that is 1462 Leetcode medium course schedule 4. Right, so there are a total of num courses you have to take labeled from 0 to num courses minus 1. You're also given an array prerequisites where prerequisites of I is equal to AI comma BI, which indicates that you must take course AI first if you want to take course BI. So this is basically indicative of if we are taking course BI, we need to ensure that we have already completed AI that course, because it is a prerequisite. So you see this is a directed graph that will be formed when we have certain prerequisites. If we have to complete CI, we also need to complete BI, and before BI we need to complete AI. So this is basically what we are given here. For example, the pair 0 comma 1 indicates that you have to take course 0 before you can take course 1. So 0 comes first and then 1. So there will be a directed edge from 0 to 1, right? Now prerequisites can also be indirect. If course A is a prerequisite of course B and course B is a prerequisite of course C, then course A is a prerequisite of course C. So that means we have transitivity. So if A is a prerequisite of course B, and if B is a prerequisite of course C, that means A would be a prerequisite definitely for course C. So this implies transitivity, right? Transitivity. I mean transitivity, right? You're also given an array queries where queries of I is equal to uj comma vj. For the jth query, you should answer whether course uj is a prerequisite of course vj or not. Return a boolean array answer where answer of I is the answer of the jth query. So true if in case uj is a prerequisite of course vj, and false if it is not. So that is our problem. Let us say this is the example. Let us see the example 1. So 1 comma 0, number of courses is 2, prerequisites is 1 comma 0, you can see. So that means there's an edge from 1 to 0. Now we check 0 to 1. So basically this is asking if in case there's an edge from 0 to 1, which is not the case. So it would return false. And next it asks 1 to 0. Is there an edge from 1 to 0? Yes, there is. So that would return true. Right, so false and true. This is the answer. The pair 1 to 0 indicates that you have to take course 1 before you can take course 0. Course 0 is not a prerequisite of course 1, but the opposite is true. Right. And then we have another example. You can see that query, this is example 3, right? So we have prerequisites 1 to 2, 2 to 0, and 1 to 0. Queries 1 to 0, yes, this will be true because 1 comes before 0 in the directed graph. That is, it is the parent of 0 if you talk about it in other words. So it is reachable from 0 is reachable from 1, right? But the other way around, it is not true. So if you were asked 0 comma 1 as a query, that would be false. Now 1 comma 2, yes, 2 is also reachable from 1 because there's a directed edge from 1 to 2, right? So that would be true. Now let us get to our solution. So this is the solution that I have posted. That is, we'll be using Kahn's algorithm, that is the topological sort. So BFS based topological sort to maintain a mapping of all the prerequisites for each course, right? So our approach is basically something like this. Firstly, we build our graph, that is create an adjacency list from the prerequisites and track the in degree for each course. Since we are applying topological sort, we need to track the in degree of each node. Now push all the courses with in degree equal to 0 into Q, that we do in our basic Kahn's algorithm. For each node popped, that is for each neighbor, for each of the node popped, we check each neighbor, mark the node as a prerequisite of neighbor, right? Since node basically has its neighbors, we are going to reach neighbor only when we have reached the node, right? So if our neighbor is getting reached, that is, if our neighbor is reachable from node, that means the neighbor's prerequisite is actually node, right? Since there's a directed edge from node to neighbor, so we mark the node as a prerequisite of neighbor in our map. And we also are adding all the prerequisites of node because it is a transitive policy that we are following, right? So let us say this is our node and this is the neighbor that we are going to, right? And there are some nodes, other nodes 1 and 2, that were the parents of this or the ancestors of this particular node, right? So neighbor already has node as its prerequisite, but since these are the prerequisites of node, that means that we need to complete this node first, right? This course first. And this course itself has the prerequisites 1 and 2, right? So these are the prerequisites of node as well as the neighbor, right? Because these are the ancestors of node and neighbor both. So we basically add all prerequisites of node due to transitivity, and decrease in degree of neighbor, push it if it becomes 0, right? So that is the standard Kahn's algorithm. And for each query, we check if U is a prerequisite set of V and return true or false based on that. Now complexities, let us discuss that. So building the graph takes O of V, where E is the number of prerequisites, and topological sort takes O of V plus E times the V. That is because we are going over all the Q queries because we copy the prerequisite sets, and query answering takes O of Q, where Q is the number of queries. Space complexity is O of V square in the worst case. Dense prerequisite relationships, we have V times V number of vertices being traversed. sorry, maintained in the space, right, in the adjacency list. So now we are using trans-sort for our solution. So this is check if prerequisite, our main function, which takes num courses, that is the number of courses, then prerequisites, vector of int type, and similarly queries. Now we declare our adjacency list in the format of an unordered map. That will be storing our course u, and it will be going to our v, all the vectors that we can go to, all the nodes that we can go to. So u2, v1, v2, v3, and similarly. So this is the format of the adjacency list, and vector of int in degree is going to store our in degrees for each of those nodes. So the size is number of courses, that is n. So we go over all the prerequisites. That is, we are going to be forming a directed unweighted graph. So u is e of 0, v is e of 1. Adjacency of u dot pushback v. So there's a node from u to v. So we add it into our adjacency list and increase the in degree of v because there's an edge from u to v, right? So in degree of v would increase. So we have done that here. Now we declare a queue of int type, and for all those nodes that have an in degree of 0, that is, those nodes are going to be our starting points, right? So these are the nodes which have no parents or no ancestors, 0 and 2 in this example, right? So these are the nodes actually going to be the nodes that we are starting from. That is why we push it into the queue. These have in degree equal to 0, right? We've done that. Now we maintain a prerequisite map to track our prerequisites. So unordered map of type int, unordered set of int prerequisite map. So basically we're going to be storing our course, that is a node, and the prerequisites of it, all the prerequisites of this particular course. So basically node and its ancestors, right? So this problem can also be identified in this format, that we are storing the ancestors and of that particular node in this format, and we're using an unordered set because we don't want to store the same values in it again, right? So this is the format, and basically we check while the queue is not empty. That is our standard VFS approach, or toposort. For toposort, we extract the node from the front of the queue and pop it out from this queue, and check for each neighbor in the adjacency list of node, right? We check for each neighbor. If the basically for each neighbor we add that for that particular neighbor, right, we add the node, because node is our ancestor of neighbor, that is the parent of this particular neighbor. So since node is the prerequisite of neighbor, since there's already a directed edge from node to neighbor, we add the prerequisites of the node as well now. So that is, the prerequisites is basically the parents of this particular node, right? So node would be reachable from these parents as well. So we add the prerequisites of the node as well by transitivity. They have prerequisites of neighbor as well. So auto prerequisite in prerequisite map of node, we insert for our neighbor the prerequisites of the ancestors as well. So neighbor would be storing not just the node but its parents as well, as I told you that we have transitivity. So the parents would also be included. Parents would be the ancestors of node, right? So in this format we'll be storing it, right? And now we check by reducing the in degree by 1 and push of 0. So if the in degree, we reduce it by 1, and if in degree of the neighbor comes out to be 0, we push it into the queue. And then finally we have our length of query. Length is basically query store size. We maintain a vector of bool type, that is result, which is going to store our final result, that is true or false. So we go over all of these queries, and source would be our starting node, that is queries of I of 0, and destination is the point we need to reach, queries of I of 1. Now reachable is going to be storing our true or false value. So if the destination node has prerequisite source, then it is reachable. So basically, if the source to destination, if it is possible, that is, if from the graph there's a topological sorting, that is making sure that there's an edge from source to destination, then we mark it as true. Otherwise, we mark it as false. Dot contains would basically result true or false. So if the prerequisite map of destination, that is this value, if it contains source, right, there can be other nodes as well. So if the prerequisite map of destination, that is this value, contains source, it would return true. Otherwise, if it doesn't contain, it would return false. And we store it here, and we finally return the result. So that's it about the problem.